It's often easier to find the probability of an event given that some other event has occurred. For example, the probability a president will try to establish a dictatorship, well, who knows? But the probability a president will try to establish a dictatorship, given that they are a narcissistic con artist, is probably easier to estimate. So we'll want to find a way to find the unconditional probabilities from the conditional probabilities. Suppose we can condition event A on mutually exclusive events B1, B2, and so on, where exactly one of the BIs must occur. Then the event A is going to be the union of the intersections of A with each of the BIs. Since the BIs are mutually exclusive, these intersections are also mutually exclusive, and so the probability of A is going to be the sum of the probabilities of the intersections. Now, from Bayes' theorem, we know that the probability of a given BI is the probability of the intersection divided by the probability of the BI, and rearranging things we have. And consequently, this sum of probabilities can be rewritten as this gives us what's known as the law of total probability. Suppose A is conditioned on mutually exclusive events B1 through Bn, where exactly one of the BIs must occur. Then the probability of A is going to be the sum of the products of the conditional probabilities and the probability of the condition. For example, suppose a bag has 3 coins. 2 are fair, and 1 has heads on both sides. A coin is picked for the bag at random and flipped twice. What's the probability it lands heads both times? So there are 2 possibilities. Either the coin is fair, or it has heads on both sides. But in either case, we can find the probability it lands heads twice. If the coin is fair, the probability it lands heads on any one flip is 1/2, so the probability the fair coin lands heads twice will be But if the coin is unfair, the probability of heads is 1 since it always lands heads, and so the probability it lands heads twice is also going to be 1. Now, since there are 2 fair and 1 unfair coin, it's reasonable to conclude that the probability the coin is fair is 2/3, and the probability the coin is unfair is 1/3. And so using the law of total probability, the probability of 2 heads is the probability of 2 heads given that the coin is fair times the probability the coin is fair, plus the probability of 2 heads given the coin is unfair times the probability the coin is unfair. And filling in those values we get. Now, we can organize these probabilities using a tree diagram. We really should call it a path diagram because trees don't typically grow sideways, but mathematicians aren't arborists. And the thing to remember about a tree diagram is the branches are the conditions. So we're conditioning on whether the coin is fair or unfair. We note that we choose either the fair coin, probability 2/3, or the unfair coin, probability 1/3. And so that forms our first split. If the coin is fair, there's a probability of 1/4 that we get 2 heads. And so we can take that path, and we really don't care about any of the other paths from this point. If the coin is unfair, there's a probability of 1 that we get 2 heads. And then we'll multiply along the branches to give the probabilities. And then adding gives us the total probability. Now, while a path or tree diagram is a useful way of organizing it, if you have too many different ways that we could condition the event, it does become a little messy. So it's best to focus on the algebraic formulation. So, for example, suppose a medical study consists of 150 people in good health, 75 in moderate, and 25 in poor, and the probability of having a cardiac event is 0.1, 0.3, and 0.8 respectively. Let's find the probability a person in the group has a cardiac event in the next year. So we'll go ahead and set up some events. Let G, M, and P be the event a person is in good, moderate, or poor health, and C the event a person has a cardiac event. Now there's 250 people altogether, so the probability a person is in good health is, the probability a person is in moderate health is, and the probability a person is in poor health is. We're given the probability of a cardiac event for each of the three cases, and so our law of total probability tells us that the probability of the event is the sum of the products of the conditional probability times the probability of the condition. And that will be, and remember, a useful strategy for learning and understanding mathematics is to solve it again. So, treating our probabilities as frequencies, we'd expect that 10% of 150, 15 cardiac events among the patients in good health, 30% of 75, or 22.5 cardiac events among the patients in moderate health, and 80% of 25, 20 cardiac events among the patients in poor health, for a total of cardiac events out of 250 patients, so the probability of a cardiac event will be, which is consistent with what we found earlier.